Zhu, could you
Yeah, that's
please,
me.
could you please try to share your slides,
Sure.
your screen? Yeah, okay, you're already there. So let me see. We still have 4 minutes. Okay, we can start.
Okay. So good morning, people. So I'm going to present our measurement of transverse single spin asymmetry at variable rapidity at star experiment in PP collision at 200 and 500 eV. Oh, okay. So due to the limit time, I will quickly go through the motivation, experiment analysis, and focus on the results and discussion. And our paper has been accepted in PhD. So for the time being, only the archive is available. So, but it will quickly go to PhD. So first, we have been discovered the transverse single spin asymmetry for a very long time. So we did all kinds of experiments to repeat this phenomenon, and we keep doing this. And after years, we developed some sort of theoretical framework to explain this phenomenon. So, for example, we have the TMD. So, like in other frameworks, it divided the total effect by two parts. One comes from the initial state, one comes from the final state. So usually when we measure the Pion TSSA, we are measuring both effects due to these frameworks. So since we are measuring pi0 TSSA in our measurement, we are thinking to use other observables like the jet TSSA and the Collins asymmetry, which are sensitive to different effects, so that we can have a full scale of the whole TSSA. So we're doing the experiment on week, which have the polarized proton beams, and start experiment lies in here, 6 o'clock. So zoom in for the star detector. We mostly use this sub-detector called FMS, the forward meson spectrometer, which actually is a EM calorimeter, and it has more than 1,000 blocks like this. So it covers the forward pseudo rapidity from 2.8 to 4.1, and it has 2 cell size, so that we can measure the high energy pion, which get closer to the beam pipe. So the data we use is from 2011 and 2015, which are 500 and 200 GeV, and with above 15% polarization. And all the data are triggered by the FMS itself. So the principle is simple. So we measure the number when the spin is in one direction, and the number when the spin is in the opposite direction. And after some formula that we use to lower the uncertainty, and then we can calculate the AN, which is the TSSA. So after that, we also have some more work. So for example, this is the Pion mass spectrometer, and we have a signal here, and you can see the background is very high, so we need to do a subtraction. So after that, we can get the wanted AN. So for the jet analysis and the Collins asymmetry, the procedure is similar with a little bit modification. I'm not talk about this in detail. And I just want to mention again, the jet here we measure, it's a EM jet, since we only have a EM calorimeter. So we don't have the hadronic part. And we also estimate the uncertainty and do some corrections to make sure everything goes in place. And we're not going to discuss the details. So this slide is the catalog of what we measure. So we have the Pion TSSA, which we have 3 parts, and the jet TSSA and the Collins asymmetry, so which are sensitive to initial plus final state effect, the jet to initial state, to the Collins state to final state. So let's see the results. So this is the Pion TSSA. So we have 2 different energy, which is the blue and the red points, and we also offer some theory prediction here. So mostly we can see that the trend is the AN is rising as the XF, which is the PHENIX. So if we compare the theory curve, so for some parts it looks okay, but sometimes we have discrepancy. But I will show you that we can discuss in another observable that would be more apparent to this problem. So first, let's put our results into all the other Pi0AN measurement over the years. So we got a bunch of them in different experiments. So we have this lowest energy from 20 GeV, and the highest energy is 500 GeV. So if we create a band here, we can see that in some extent they are consistent to each other, so they have the same trend. And also we need to take a look at this period star data, which was done in 2008, so in 200 GeV. So if I take a look at these points, these circle points, open circle points here, so you find that in lower XF, they are lower than our results in 200 GeV. So we will show you later that's because of the PT dependence. So the PT of our experiment here, it's quite high comparing to the previous one at low XF here, lower than 0.4. So after that, the PT begins to higher than ours. So the AN result also begin to be higher than ours. Yeah. So so we're talking about a PT. So this is the AN versus PT. We have 3 different panels, which is for 3 different XF range. For each XF range, we plot the data for 200 GeV and 500 GeV. So for the 500 GeV, the statistic is not very high, so we do not get too much information from this. So it's just a flat distribution around PT maybe. But for 200 GeV, we can see that very clearly the PT rises as PT. Oh, sorry, the AN rises as PT. So at least from what we can measure, like say for in the first panel, below 3 GeV, it keep rising. But after that, we have other measurements at start that telling us these are not going forever, rising forever. It will saturate somewhere in high PT, but since we limited our measurement at certain XF range, so we cannot draw those points because of it. So since we have this from, for example, from 2 GeV to 3 GeV, the PT dependence very strong. So take a look at here, comparing this circle points. So from 1 to 3 GeV, that's the order. So we have higher PT, so essentially we have higher AN. So this plot will explain why our results it's higher than the previous star result at 2008. So also if we look at this theory curve here, we can see that it does not have very good description about this PT dependence behavior. So that's why if we have this XF and PT, we have 2 variables, it's hard to get a very good description of the data from the theory curve, since we already have a bad description in the PT spectrum. So that's what we learned from this classical Pi0 measurements. And during our research, we also find interesting things for the pion. So we found that if the pion tends to be standalone with no other energies nearby, its AN would be different. So we create this definition of isolated pions, which we require in the eta phi space at certain area. So if the pion in this area takes 98% of the energy, then we call it isolated pions. So you can see that as the XF increase, this isolated pion actually would become more and more and dominate at very high XF. So let's take a look at the isolated pion and the non-isolated pions. So it clearly has higher AN for the isolated ones. So the solid points here. And we just talked about the AN of the whole sample, whether it's isolated or not, we just take it as a whole sample. And so if we compare to this, we're going to find that there should be two mechanisms for these two types of pions. So if we combine them into this simple plots here, it might be not fair to do a comparison to theory, because we are not quite understanding what is this isolated pions. Well, we can call it some origin like diffractive, but also we do not know too much about diffractive. So that's something that I think in the future people.
Zhanwen, you have 3 more minutes.
Yeah.
You have 3 more minutes.
Oh, sorry. Okay. So okay. So that's the story of the pions, and then we have the measurement of the jet. So the jet here, the trend looks similar to the pions, increase with the XF, but the magnitude is much more smaller because if we take a back look at the pointer, so it's 0.05 or 6, so it's 0.01 here, so it's much smaller. And we also separate the jet into two types. So one with the multiplicity, which also means the photon numbers larger than 2. The other not without this requirement. So we do this because if we have two photons, which might be a pion, so like isolated pions. So this kind of pion has very high AN, so we want to isolate them and see what happens. So clearly, the AN would drop after we exclude these high AN isolated pions. So that's why we separate them into two types. And we also have the ND result, which is also done in RIC at 500 GeV. So compared to us, it's consistent, although our statistics were limited. And by the way, they are constructing the full jet, and we are doing the EM jet. So kind of consistent here with the black points. So the final measurement is for Collins. So these are the results. So at the left plot, so they're consistent to 0 for both energies. And the theory gives the impression that they also include this AN equals to 0 line. So consistent because they have very large uncertainty. And we also do something called the JT dependence. The JT is the transverse projection for the pion on the jet cone. So we did this because in the Midrapidity analysis for the Collins, so they discover some dependence of the JT. So we do the same thing to see if we have the same phenomenon. So the results showed us that we found very weak JT dependence, weak but not 0. So that's what we found here. So in the end, I'm not going to read this summary. So we did full scale measurement on the AN phenomenon of pions and jet and Collins asymmetry. So just to understand better the origin of the AN. Yeah, so I finished. Thank you.
Thanks, Zhanwen, for a very nice presentation and finishing just at the right time. So the talk is now open for questions. Please raise your hand if you have a question. I don't see any raised hands here. Anybody having a question, please raise your hand. Yeah, April, please go ahead.
Yeah, I just I found the isolated pion having a higher ASIN really interesting. I was just wondering if if that had been seen by anyone before, or if that is completely new, and if so, if there's any other related studies that could help give more information about it.
So I think we report this not in the paper, but in talks a few years back. That I think nobody measured this before us, I think. So this is new.
Okay, so if there are no further questions, let us thank Zhanwen again and let us move to the next talk.
Thank you.
Which is, oops.
Okay, sorry.
Which is by Nicole Lewis. Hello, Nicole.
Hello.
And could you please, no, this is not your screen, right?
Can you see my slides?
Yes, we can see your slides and you can start, please. So I will give you warning at 12 minutes and you have in total 15 minutes. Please start.
Okay, great. Hi, everyone. I'm going to be giving a talk on new transverse single spin asymmetry measurements of mid-rapidity direct photons and neutral mesons at PHENIX. So we already had an introduction to this, so I'll go through it pretty quickly. But in this context, we're talking about an asymmetry measurement between one transversely polarized proton and one unpolarized proton, and then measuring the asymmetry of particles that travel to the left versus the right. And there have been perturbative calculations that looked at effects only from high energy parton scattering and showed that these spin momentum correlations should be very, very small. And of course, they're not very small. We've already seen this morning and we'll continue to see throughout this session that they are indeed larger asymmetries than what has been predicted. So as we already saw, there are two different frameworks for analyzing these. There's the transverse momentum dependent framework. So these are two scale functions. They depend both on the hard scattering energy and then also this small non-perturbative transverse momentum of a parton. And I should mention that all of the results that I'm going to be showing in this talk are inclusive. I'm only measuring a single particle in the final state and therefore not sensitive to this soft scale transverse momentum. And therefore, in order to apply these transverse momentum dependent functions, we need to take the KT moment of them. And as we already heard, these effects can be broken down into the Sivers effect, where there's an initial state transverse momentum dependent function in the transversely polarized proton, and also the Collins effect, where the transversity function is convolved with the transverse momentum dependent Collins function for the final state. And as we previously saw, the Collins effect has been measured to be much smaller than the Sivers effect. The other framework are these collinear twist-free functions. So these are single scale functions. They only depend on the hard scale of the they're collinear, so they depend on the hard scale of the interaction, but no soft non-perturbative transverse momentum. These are multi-parton correlations. They capture the spin momentum correlations due to quantum mechanical interferences between scattering off of one parton at a given x versus scattering off of a parton of the same flavor and same relative x plus an additional gluon. And so these come in two different types. There's the quark-gluon-quark correlation functions. So that's scattering off of a quark and a gluon versus scattering off of a single quark. And the tri-gluon correlation functions, which are sometimes referred to as the three-gluon correlation functions. So that's scattering off of two gluons versus scattering off of one. And the language that I've been using in this slide more relates to initial state, sort of these parton distribution function like quark-gluon-quark and or three-gluon correlation functions, but there are also final state twist-3 functions. Okay, we already heard about RIC. This is the relativistic heavy ion collider, the only collider in the world that is able to run polarized proton beams. The experiment that took these measurements is called the PHENIX detector. Right now, we're looking at the central arms. We're looking down the barrel of the beam. The next talk by Dillon is going to take you through a much more detailed description of this diagram for these measurements. These are photon measurements. So they utilize the electromagnetic collider, which are these 8 segments on the outside. 6 of these segments are made of lead scintillator and the other 2 are made of lead glass. So I'm going to start with the pi0 and eta transverse single spin asymmetries. So in the previous talk, we heard about forward pi0 measurements. And so that's forward relative to the polarized proton. And so that is mostly sampling that polarized proton at higher x. And so that production mechanism is dominated by valence quarks in the polarized proton. At Midrapidity, the production mechanism is a little bit more complicated, but you can see that it is highly sensitive to the gluons in that polarized proton for a very wide range of PT. So here is the Midrapidity transverse single spin asymmetry result. You can see that it's consistent with 0 to within 10 to the negative 4 at low PT. And this measurement was done with the final polarized proton data set from PHENIX. So it's really nice to have something that is so precise. It's a factor of 3 increase in precision when compared to the previous result and reaches higher in PT. And these results were recently published in this paper on PRD. Here is the eta result. It's also sensitive to strangeness within the twist-3 functions. It's consistent with 0 to within about 0.5% at low PT, and also shows this increase in precision by a factor of 3 and also reaches higher in PT. If we're comparing these results to theoretical predictions, so here is the same pi0 transverse single spin asymmetry result. This purple line is the quark-gluon-quark correlation function contribution. This is a function, this prediction includes effects from both the initial state and final state. And Daniel is actually giving a talk on this tomorrow morning that will go through this in much more detail. So I recommend going to that. The other 3 curves here are done using the Sivers function in what's called the generalized parton model. So that's a function that that's a framework that takes the KT moment of the Sivers function and also doesn't include next to leading order effects from interacting with the proton fragment. So that is this red curve right here. And then the other 2 curves are in the color gauge invariant generalized parton model, which sort of expands on this model and includes a 1 gluon exchange in both the initial and final state. And so there are 2 scenarios that maximize and minimize the asymmetry. And you can see that we have the statistical precision to distinguish between these 2 scenarios at lower PT, favoring scenario 2. Switching gears now to direct photons. Direct photons come directly from the hard scattering event, and therefore they are only sensitive to initial state effects. They don't include any effects from fragmentation. And as you can see from this plot, at mid-rapidity, the production mechanism is dominated by quark gluon to quark photon. And so this is a uniquely clean way of extracting gluon PDFs. It's sensitive to the gluon dynamics in the proton at leading order. As we've already seen in this talk, there are a lot of other photons in an event that are not direct photons, many of them coming from hadronic decays. And so the first step towards isolating direct photons in your sample is to subtract out photons that are tagged as coming from either pi0 or eta decays. So we take our photon in question and we match it with other photons in the same event. And if they reconstruct either a pi0 or an eta, they are eliminated. There's also an isolation cut. You take the photon in question and then you look at all the other measured tracks and clusters that are in the same event within a cone of 0.4 radians. And we require that that cone be less than 10% of the photon's energy in question, of the photon in question's energy. And this cut not only further eliminates the contribution from decay photons, but it also serves to lessen the contribution from next to leading order fragmentation photons. So here is the direct photon result. This is the first time that the direct photon transverse single spin asymmetry is measured at RIC. It's actually the first result for this asymmetry in 50 years. You can see that it's consistent with 0 to within about 2%. And here are the predicted contribution from the quark-gluon quark correlation function, which includes effects from both the polarized and unpolarized proton. You can see it's predicted to be very small. And then the tri-gluon correlation function contribution can be seen in these blue and red lines. And you can see that at low PT, especially, we have the statistical precision to start constraining this tri-gluon correlation function. And you can read more about these results that have been posted on the archive. So this brings me to my conclusion. Transverse single spin asymmetry measurements probe the parton dynamics in the proton as well as in the process of hadronization. There are two different frameworks for analyzing these, the transverse momentum dependent and the twist-free correlation functions, where the twist-free correlation functions only require being sensitive to a single hard energy scale in order to measure them directly. I showed the pi0 and eta transverse single spin asymmetry results, which are consistent with 0 and have a factor of 3 higher precision. They're sensitive to both initial and final state effects for both quarks and gluons. The direct photon transverse single spin asymmetry was measured for the first time at RIC. It is also consistent with 0 and it's cleanly sensitive to the gluon dynamics in the transversely polarized proton.
Thanks, Nicole, for a very nice presentation and also for finishing before time. So we have a lot of time for questions. I think April, this raised hand is from previous talk. Now I don't see any new.
Oh, it's new. I have a question.
You have a question. Yeah, please.
Yeah. So I was wondering, could you go back to slide 11? So I was, could you explain where the plot comes from? Like, is that a theoretical calculation or?
This is a theoretical calculation that was first produced for this PHENIX paper.
Okay. Do you know any details about like how it was produced? Or I can go back and look at the reference if you don't.
Don't remember any details.
Okay, that's fine. And then could you also go to the previous slide with your results plot? Yeah, so I was trying to understand it. So you mentioned the tri-gluon function, but I don't see a tri-gluon curve on the plot. So could you just explain again what's shown here?
Yeah, there isn't one. We contacted the people who produced this paper, but unfortunately the person who was in charge of the code for the pi-0 transverse single spin asymmetry had left the field. And so it wasn't something that was feasible in the time that we needed to get this paper out.
I see. Okay, but it could also be included. It's
yes,
as an additional.
Yeah, a full,
okay.
Which I should have mentioned. I'm realizing now that I forgot to mention. So thank you for your question. A full twist-3 description of this transverse single spin asymmetry result would definitely need to include the twist-3 tri-gluon correlation function. Yeah, okay. And this result should be able to help constrain that function.
Okay, thank you.
Zhanwen?
Yep, so I want to ask, so all the theory that try to predict the AN in the forward rapidity, so it has to be very small at mid rapidity. And I also noticed this theory from reports, they also are very small. So I just wonder the usual one that account for the high AN at forward rapidity. So how low are they comparing to these models in your plots at mid rapidity? Am I making sense?
I think so. I'll answer, and then you can tell me if I didn't answer your question. So the reason that we think that the asymmetries are much larger at forward rapidity versus mid rapidity, and this is something that has been consistently measured, is because the production at forward rapidity is dominated by valence quarks in the transversely polarized proton versus at mid rapidity, where you're probing at more moderate X, and therefore you have a lot more effects from gluons and even anti-quarks. And we've consistently seen through transverse single spin asymmetries that are sensitive to these gluon spin momentum correlations that they tend to be smaller. Did that answer your question?
Christine, sorry, yeah, go on.
Yeah, so I understand, so it's sensitive in mid rapidity. Anyway, I just don't know the actual number, like magnitude, how many magnitudes smaller, like something like that. Yeah, it's okay if you cannot give an answer to that.
Yeah, Christine has typed a comment in the chat box. That is the direct photon particle contribution functions in 2010 were published by Werner Vogelsang. I think this is correct at next to leading order. Any other question? So I have a question. So you were showing this direct photon result. Could you please go to that slide? This result is consistent with 0, but to the theory predictions within, so the upper and lower theory curve are the error bars, right? Within the error bars, theory error bars.
So what they found in this paper was that
okay.
Yeah, so this is maximizing and minimizing the possible asymmetry based off of, so there's a symmetric and anti-symmetric function that these tri-gluon correlation functions can be broken down into. And so this is, one of these curves predicts if they have the same sign, and then one of these curves predicts if they have the opposite sign.
Okay. It's very nice result. Anyone else has a question? Okay, if not, let us thank Nicole once again. And let us move to the next talk, which is by Dillon. Okay, great. So please start.
Just want to make sure that you can see my slides really quick. And I'm going to get into full
Yes,
screen.
we can see your slides. It was very quick.
Excellent. All right, I will go ahead and get started. So thanks for having me. Hello, everyone. My name is Dillon Fitzgerald, and I'll be speaking on behalf of the PHENIX collaboration about transverse single spin asymmetries of open heavy flavor electrons and charged pions in 200 GeV mid-rapidity collisions at PHENIX. So before talking about the measurements, I want to talk a little bit about spin physics and proton structure, of which our understanding has really evolved greatly in the past few decades. For instance, we now know that valence quarks do not carry all the proton spin. We also have to take into account the spin of quarks and gluons, as well as valence quarks, or as well as C quarks, and their orbital motion. So this introduces some interesting questions like how is the spin of quarks and gluons correlated with the proton spin, or how is the orbital motion of the quarks and gluons correlated with the proton spin? And these questions have led to the development of more detailed or descriptive initial state non-perturbative functions, where things like where extra degrees of freedom, such as the nucleon polarization, quark polarization, or quark transverse momentum are taken into account to help describe some of these correlations. So we're also interested in how to access these spin momentum correlations and spin-spin correlations from data, which we have observables such as transverse single spin asymmetries that are sensitive to such things. So this has already been described in some detail in the previous talk, so I won't talk about it too much, but I will just quickly recap that these transverse single spin asymmetries were predicted to be very small by perturbative QCD calculations, yet persisted to be large in measurements across several laboratories. So this actually implies the existence of non-perturbative spin momentum and spin-spin correlations within the proton, which is quite interesting. So people got to work in trying to describe these large TSSAs from a theoretical point of view. So there's two frameworks in which these can be described. One is higher twist effects. And as was mentioned in previous talks, this is collinear, so we only need one hard scale. And we access this via the PT of the measured particle. And I should just mention here that this is the effect I'm going to be focusing on because we measure A sub n as a function of PT. We're sensitive to these type of observables. So in the higher twist framework, you need higher twist effects. For example, twist 3 to describe observed TSSAs. And when I say higher twist, I mean power suppressed terms in the factorization expansion. So twist 3 is suppressed by 1 over Q. And diagrammatically, essentially what this is a quantum interference between the 2-to-2 process and the same process with an extra gluon with similar X. And that extra gluon, for example, can come from the initial state nucleon. So these can also be described in transverse momentum dependent function framework. And in this framework, there's explicit dependence on the transverse momentum of partons within the proton, where we need access to both a hard and soft scale with sufficient scale separation. And what's nice is there has been some success in unifying these two frameworks. So as shown at the bottom of the slide here, on the left, there's the twist 3 correlator, the quark gluon quark correlator, which has been described as factorial KT moments of the Sivers TMD PDF, as mentioned by Nicole in the previous talk. So as I mentioned, I'm going to be focusing a bit more on twist 3 correlators. So I just want to describe this in a little bit more detail. So I have a cartoon figure at the top here that corresponds to my equation at the top right. And really what I want to point out here is that the terms with an A and B in the subscript are describing initial state effects. The terms with the C in the subscript are describing final state effects. And the terms with the 3 in the superscript are for twist 3 correlators. And the idea is that, so this is quite a long equation, but if we measure A sub n for different final state particles, then it actually gives us access to specific terms in the sum, different final state particles at different kinematic regions. So for example, heavy flavor electron production is dominated by gluon-gluon fusion at 200 GeV mid-rapidity collisions. And what's nice about this is the gluon transversity distributions are actually equal to 0. So that's these lowercase delta Q distributions. They're equal to 0 for gluons, which means that these last two terms in the AN formula actually go away for gluon-gluon fusion dominated processes. And this gives us access to the trigluon correlator. In addition, looking at charged pion production, this is dominated by quark-gluon scattering at 200 GeV mid-rapidity, which gives us some sensitivity to quark flavor for different initial and final state effects. Okay, so these type of measurements are allotted to us by the spin physics program at the Relativistic Heavy Ion Collider, but we've already seen this in some previous talks, so I'm going to go ahead and talk about mid-rapidity charged particle detection at PHENIX. This is, again, a mid-rapidity measurement, so we're just talking about the central arms. This is transverse to the beam pipe that you're looking at here. And the acceptance, the azimuthal acceptance is 0.5 per arm on either side of the beam here. And the pseudo rapidity coverage is just a narrow wedge at absolute value eta less than 0.35. Tracks are fitted with hit information from the drift chamber and the pad chambers, as well as the VTX. And this is how we get a measure of momentum. The ring imaging Cherenkov detector is used for particle identification. It has a Cherenkov threshold of gamma equals 35, corresponding to a momentum of 20 MeV per C for electrons and 4.9 GeV per C for charged pions. This actually gives us quite a large momentum region where we have good E-pi separation, which is going to be very important for these measurements. In addition, the EM-Cal measures energy deposits. This was already nicely described in Nicole's talk. I just mentioned additionally that we have triggers that are used to select select electrons and charged pions from the EM-Cal. And finally, the hit pattern is measured by the VTX. This is the silicon vertex detector close to the beam pipe. And here, this is used for the heavy flavor electron analysis because we require a hit in the inner two layers of the VTX in order to veto photonic electron conversions. So now that we've talked about how these particles are detected, I want to talk a little bit about how this measurement's done at PHENIX. So it's calculated using the so-called relative luminosity formula, where we integrate over the azimuthal ranges of the east and west arm. And in this formula, R is the relative luminosity. It's just the luminosity, a ratio of spin up for spin down bunch crossings. We have a correction factor due to the fact that we're integrating over the azimuthal range, correcting for the polarization of the beam. And then the left subscript is just, the L subscript is for the left arm. This is done, there's an equivalent formula for the right arm as well. And the up versus down just tells you the spin of a particular bunch crossing. And once this is measured for our candidate sample, we can extract our signal measurement by subtracting away the background. So we know how to quantify the background sources. So for the heavy flavor electron measurement, the background sources come in 3 flavors: photonic, non-photonic, and hadron contamination. All of the photonic background sources, actually the asymmetries have been nicely measured to be 0, all by Nicole Lewis, which was just shown in the last talk. So this is just treated as a dilution. For the non-photonic sources, we have Ke3. These are Dalitz decays from kaons, but it contributes a negligible fraction, so it's not considered in our background correction. J psi is considered though, and we take this from a previous PHENIX measurement, and it does contribute a large source of statistical uncertainty, which I'll comment on in a bit. This is actually why we chose to do the background correction separately for open heavy flavor signal and non-photonic, where the only difference is that we don't include the J psi correction in the non-photonic results. And then finally, we've taken the hadron contamination from a previous PHENIX measurement as well. I have listed here some cross-checks and systematic studies, which I won't go into for sake of time, but it's listed for your reference. So a bit about open heavy flavor production before talking about the measurements. So open charm production is dominant contribution in this kinematic range. And furthermore, heavy flavor production is dominated almost entirely by gluon-gluon fusion in this kinematic range, which is nice because the trigluon correlator, as previously mentioned, is not well constrained from previous measurements. So here we have just an image of the different contributions from this trigluon correlator. In addition, heavy flavor production has a small contribution from anti-quark annihilation, in which case there are contributions from this quark-gluon-quark correlator, or Efremov-Terryevsky-Sterman correlator. And this is somewhat constrained from previous measurements, so we can actually use this as an input to constrain the trigluon correlator. Okay, so without further ado, I'll present the measurements. So here I have the charge combined open heavy flavor electron A sub n. So this is the most precise measurement of open heavy flavor and non-photonic electron transverse single spin asymmetry that's been measured. This was done at mid-rapidity. And as you can see, it's consistent with 0 over the measured range. And I just point out again that so we have in blue open heavy flavor and in green non-photonic data points, which are fairly consistent until the last PT bin, where the large systematic uncertainty for the J psi result actually has a pretty large effect. So if this is ever improved upon in the future, it'll be quite easy to better constrain the open heavy flavor result as well. So we've also looked at this for separate charges, and I point out that this is also consistent with 0 over the measured range. But what's more interesting is actually to look at the open heavy flavor results separated by charge in comparison with theoretical predictions. So these are coming from PRD 78, a paper by Kang, T, Vogelsong, and Yan, where they quantified the transverse single spin asymmetry for D zeros at 200 GeV RIP kinematics. And I've taken this parameterization and done a simulation to decay it into a decay lepton and plotted the asymmetry along with the results that we've received from data. Something that I want to point out that's quite important is the ordering of these curves is actually different for the separate charges, which gives us some sensitivity to constraining these lambda parameters. And a bit more about these lambda parameters, they correspond to normalizations of the tri-gluon correlators with respect to the unpolarized gluon PDF. So as Nicole mentioned in her previous talk, these tri-gluon correlators come in 2 types, this anti-symmetric and symmetric contribution with these different types of structure constants. And the different curves actually correspond to just setting these values either both to 0, equal to each other, or opposite one another. Okay, so now I want to talk a bit about our charge pion measurements. So first, to talk a bit about charge pion production, this is produced by quark gluon, gluon, and quark anti-quark 2-to-2 processes, but it's dominated by the quark gluon channel at 200 GeV and mid-rapidity, at least until high PT. So what I have shown here on the right is a plot of the partonic sub-process fraction as a function of xt. And this is shown for pi zeros. There was not a plot made for pi plus and minus, but due to the isospin symmetry and flavor content of the pi zero, we actually expect these contributions to be quite similar. So we can make the claim that for plus and minus charged pions, this is also dominated by quark gluon scattering.
Dillon,
and this is, yes?
Sorry, you have 3 minutes.
Okay, thank you. This is also dominated by quark gluon scattering. And the measured range for the charged pion analysis is 5 to 15 GeV. So we see nicely that this is actually the dominant contribution, which is great because it means we're sensitive to quark flavors when looking at the charges separately. And just very quickly, I mentioned again that pi plus, pi minus, and pi zero is an isospin triplet. So comparing A sub n in these 3 different systems is a good test for theoretical models. And this is exactly what we have plotted on the next slide here. So this is the first results of mid-rapidity charged pion A sub n from PHENIX. It's been compared with the pi zero measurement that was shown by Nicole Lewis in the previous talk, which is quite precise. And what we see is that the pi plus and minus A sub n is consistent with 0 in the measured range, but there is an indication that they behave differently as shown by the data points. So red is the pi minus and blue is the pi plus here. And we see sort of this opposite trend, which could potentially indicate a flavor dependence. So in summary, transverse single spin asymmetries provide access to non-perturbative spin momentum and spin-spin correlations within the proton. Twist 3 correlators require only a single hard scale for which the measured particle's PT is taken as a proxy. We've shown the most precise measurement of open heavy flavor electron A sub n and compared with theoretical predictions. We've shown the first measurement of pi plus and minus A sub n at mid-rapidity at RIC. And both results presented are actually in preparation for publication, so you could expect to see those soon. And I just really quickly mentioned other results we have in preparation, a forward heavy flavor muon A sub n result, which will be more statistically precise than anything PHENIX has released, and a forward charged hadron A sub n, which is quite interesting because it will show nuclear dependence as well. So that's all I have for today. I'm happy to take any questions, and thanks so much for listening.
Thanks for a very nice presentation. And the talk is open for questions. If you have a question, please raise your hand. So somehow in this online conferences, the questions are very few. I don't know why.
I suppose it's to be expected.
But I don't understand why. Okay, so if anybody has a question later for Dillon or any other speakers, even during the session, you can continue discussing it in the chat box privately if you want. Right now, I do not see any question. So let us thank Dillon once more and we move to the next talk.
Thank you very much.
Thank you. Which is by Mariyah.
Yes.
Mariyah, can you please share your slides?
Yes. So is my presentation visible?
Yes, can you make it full screen? Is it full screen?
No, I mean,
You cannot do the full screen?
no.
No. It is going out of the screen. Even right now, the lower part is not visible.
Okay.
Yeah, now it is perfect.
Okay. Good evening, everyone. Today, I would like to talk about our recent project where we have calculated the cos2phi azimuthal asymmetry within the NRQCD based color octet model using Meson as a probe in the unpolarized electron-proton collision. I have done this work in collaboration with Asmita Mukherjee and Raj Kishore, and one could find the details of our work here. So as we know, the transverse momentum distribution contains extra degrees of the freedom than the collinear periods. So they provide the three-dimensional structure of the proton. Thus, we could say that they help us in answering some of the open questions in the QCD, such as proton spin structures, as they contain all the possible spin-spin and the spin orbit correlations among the protons and its constituents. A lot of work has recently been done to extract the quark TMDs, but very little is known about the gluon TMD as they contain the multiple gauge lengths than the quark TMDs, which contains one gauge length. Here is the operator definition of the gluon TMDs. As you can see here that it has these two gauge lengths. These gauge lengths are path dependent. So that means these TMDs are not universal due to their process dependence. In the Patan model at the leading twist, we could write the gluon correlator in terms of these unpolarized gluon TMDs and the linearly polarized gluon TMDs. So these unpolarized gluon TMDs, they represent the unpolarized gluons within the unpolarized hadron. And they have some part of this longitudinal momentum and this transverse momentum. And similarly, these linearly polarized gluons, they contain the they describe the linearly polarized gluons within the unpolarized proton. These are the only two TMDs that provide the essential knowledge on the transverse dynamics of the gluon content of the proton. Various methods have been proposed to measure both these gluon TMDs in the last few years, but this linearly polarized gluon TMDs has attracted a lot of interest. So these linearly polarized gluon distributions were introduced by these people in this very article, and it was seen that it affects the unpolarized cross sections and causes the azimuthal asymmetries. It's a time reversal even function, and in the small X region, it can be with Zaskar-Williams type or the dipole distribution, depending on the gauge lengths. And the processes where it could be probed are the Drillian process and the SIDS processes. But until now, there are no experimental investigations where this linearly polarized gluon distributions has been carried out. The only thing we know about them is that they follow this theoretical bound. So corkonium production at the EIC is an effective way to extract this linearly polarized gluon distribution functions. So for in literature, we have three theoretical models where this corkonium production is defined. One is the color singlet model, color evaporation model, and the non-relativistic QCD model. In all these models, there is a two-step process. One is the formation of this QQ bar pair with certain number of the quantum numbers that could be calculated with the perturbative QCD. And second is the hadronization, where this QQ bar pair hadronizes and forms the final corkonium, like the J psi, and that part is the non-perturbative. However, in all these models, the hadronization process varies. So as we have taken the NRQCD model into the consideration for the jet psi production. So in the rest frame of the bound state, the relative moment of the two quarks is small as compared to their masses. So we could apply the NRQCD factorization theorem to the differential scattering cross section, and we could write it in terms of these two terms, where this is the perturbative short distance coefficient, and it gives the cross section in particular color, angular momentum, and the spin states. And we can calculate it using the perturbative QCD, and it contains the singlet and all these octet states. While as this non-perturbative long distance matrix elements, they describe the conversion of this CC bar state into the final state, that's the J psi. So in this very article, the authors proved H1 in the cos2 phi asymmetry in the J psi through this leading order process at Z is equal to 1. And it was further extended in this very article to the kinematical region Z less than 1, but in the color singlet model. Here in this work, what we have done, we have extended it and incorporated the NRQCD color octet contributions to the J psi production mechanism. So the process for our consideration for the jet psi production is given here, and we have using the TMD factorization, we could write the differential scattering cross section in terms of this leptonic, tensor, gluonic correlator, and these scattering amplitudes. So as we know that since at small x the proton is rich in gluons, thus the dominant partonic subprocess at next leading order for the jet psi production is this, and these are all the Feynman diagrams contributing to the scattering amplitude. Here this K prime, this is the relative moment of the heavy quark in the corkonium rest frame. Thus, we could write the scattering amplitude in terms of this equation, where this is the non-relativistic orbital angular momentum bound state wave functions, and these are the CG coefficients. This is the amplitude for the production of the heavy quark pair, and is calculated from the Feynman diagrams. And this is the spin projection operator, which is given by this very particular equation. And here, this factor, it varies for the spin singlet and the spin triplet states. As we are using the NRQCD formalism, so we do that, there is the Taylor expansion is done around K prime equal to 0, where K prime is assumed to be small. And the first term gives the S wave contributions, while the second term gives the P wave contributions. So finally, the scattering amplitudes for various color singlet and color octet states are given by these equations. And finally, coming to the asymmetry calculations, the final expression of the differential scattering cross section for our case is given by this very equation, where d sigma mu, u, and d sigma t are given by these equations, and these A0, A1s, and B1s are the various coefficients. Here, we were interested in the small x region, so we neglected the higher terms in the xb. And as we know, the cos2 phi azimuthal asymmetry can be calculated by using the this relation, and by incorporating this and doing the integration over the azimuthal angles of the J side, we could calculate the cos 2 phi asymmetry, and this was the final result for the cos 2 phi asymmetry, azimuthal asymmetry in our case. As you could see here, both in the numerator as well as the in the denominator, we have got these F1 and H1 terms. So we could say in our case, the result depends on the ratio of these two distribution functions. So to have the numerical estimates of the asymmetry, it is needed to parameterize these distribution functions. In our case, we have used two sets of parameterization. One is the Gaussian set of parameterization, and another is the Maclaurin-Vennegopalan set of parameterizations. And for the Gaussian set of parameterization, we have the different equations for the F1 and the H1. And here this F1 is the collinear PDFs. And for our case, we have used MSTW2008 PDFs, which have been taken from this reference. And for the Maclaurin-Vennegopalan parameterizations, we incorporate the equations that are in the form of these two equations. Here, QSG is the saturation scale. So finally, coming to the numerical estimates in our case for the asymmetry, we have here plotted the asymmetry as a function of pH per, here taking the NRQCD based color octet model. As you can see, this gives the maximum significant contribution to the asymmetry. And in the right panel, here we have calculated the asymmetry as a function of this inelasticity variable for two different values of the XB. We found that this black line, which is the XB for 0.01, that means at lower values of the XB, the asymmetry is maximum. And here the asymmetry is plotted as using the Gaussian parameterization of TMDs, and we have used CMSWZ set of LDMEs here. Here in the upper left plot, we have calculated the asymmetry coming from individual color octet and color singlet states using the CMSWZ set of LDMEs. This red line is the color octet contribution to the asymmetry, and here we can say that it is given the maximum contribution to the asymmetry. In the second upper plot, we have plotted the asymmetry as a function of pH per for the various set of LDMEs. And we found that this red line is the BK set of LDME, and it was giving the maximum contribution to the asymmetry. And downward in these two graphs, we have plotted the asymmetry using the two sets of LDMEs for the individual states. And here we could find that the asymmetry was maximum for 1-0 state. And here, using the SV set of LDMEs, the asymmetry was maximum for 3PJ as well as the 1-0 state. So we could conclude here that the asymmetry is highly dependent upon the set of LDMEs we chose. So here we have also plotted the asymmetry, but here we plotted it using the Maclaurin-Vennegopalan parameterizations of the TMDs for the individual states. And we also found that the 1-0, this red line, it was giving the maximum contribution to the asymmetry. And here in this graph, we compared the asymmetry using the Gaussian as well as the Maclaurin-Vennegopalan model for the two sets of saturation scales. And this red line is the Gaussian from the Gaussian parameterization, and we found that it was giving the maximum contribution as compared to the Maclaurin-Vennegopalan model parameterizations. So finally, let's conclude, and these were the findings of our work. We found that asymmetry depends on the choice of LDMEs. The asymmetry is larger for smaller values of the XB. The asymmetry found in Gaussian model was more as compared to the Maclaurin-Vennegopalan model. We also obtained the small but sizable cos 2 phi asymmetry. So it could be a useful channel to probe the ratio of linearly polarized gluon TMDs to the unpolarized gluon TMD at AIC. Thank you.
Thanks, Maria, for a very nice presentation. We have lots of time for questions. Are there any questions? Christine.
Yeah, I just wanted to, I don't think it's published yet or submitted for publication. I just wanted to point out that there's an Atlas PhD thesis measuring J-psi plus photon, with the goal of accessing a linearly polarized PMD gluon distribution in unpolarized protons. That came out in September. I can put a link to that in the chat in case people are interested. Look at that.
Atlas publication is this proton-proton collision?
It's proton-proton, but it's looking at J-psi plus photon.
J-psi plus photon. Okay. Yeah.
It's not published. It's a PhD thesis right now.
Okay.
Maybe before it's actually published, it could be an opportunity for the theory community to provide more guidance on anything.
Yeah, that will be very helpful if we get access to it. So please type in the chat box, and if possible, also send it to us by email if possible, if it is possible. Thanks a lot. That was a very useful comment. We have lots of questions. Dillon?
Hi, thanks for the interesting talk. Could you go back one slide?
This one?
Yeah, so I just wanted to, so for my own understanding, this plot on the right is essentially summed over all the different singlet and octet contributions. Is that correct?
We have here plotted the contribution from all the individual states using the NRQC color octet model. That means we have taken both the color singlet as well as the color octet states into the consideration.
Okay, great. Yeah, that's what I thought. So that's very interesting. I'm wondering also, could this be done for other types of Corconia, like Upsilon? I don't know if we'd have the kinematic reach at the EIC.
Maybe we could, but I don't know.
Cool. Well, thank you for the talk again.
Yeah, I can comment. I mean, if we have the LDMEs for the other type of Corconia, then I think a similar kind of study, I guess, can be done there.
I see. So it's that the J-psi has been studied more such that these LDMEs are already constrained as an input. Thank you.
Any other question? Christine, thanks for sharing the link. Anyone else has a question? Okay, if not, let us thank Mariyah again, and also for the nice discussions. And we move to the next talk, which is by Rajesh. Okay, so we can see your slides, Rajesh, and
can you hear me?
Yeah, we can also hear you.
Yeah.
And you
yeah. First of all, I would like to thank the organizers for giving this opportunity to speak about the Sivers asymmetry in inelastic jet leptoproduction in the EIC. This work has been done in collaboration with Umberto, Asmita, Francesco, and Christian. We have been talking about the TMDs since yesterday. These TMDs have been in the main interest of atomic physics, which includes the three-dimensional tomography of the proton, and there are 8 TMDs at leading place for both quark and gluon sectors. In this talk, I will mainly talk about the gluon Sivers function, which is F1T per G in this table. The quark Sivers function F1T has been extracted by Alexei group using semi-inclusive deep scattering, Drillian, and W5 minus and Z boson data. And the extracted U quark and D quark Sivers function from data is shown in these plots in the impact parameter space, which is B. This analysis has been done in the using zeta prescription. Alexa, after lunch, she will talk more about these results. In these plots, the bands represents the theoretical uncertainty, which is about 68% confidence level. There is another group by Torino and Collier. They have also extracted the quark Sivers function using latest cities data from Pion and Pion production. And recently, they updated their fit by incorporating the inclusive Z data from star collaboration. Carlo will talk more about on this work in the afternoon. And there is another group from Pevia. They have also extracted the Cox-Sivers function, unpolarized Cox TMD using the Dillon data and the Cox-Sivers function by using the CD's data. The density of an unpolarized quark inside a transversely polarized proton can be written in this equation, where the first term is the unpolarized quark TMD, while the F1T per P is the Cox-Sivers function. The extracted density for U and D quark is shown in this plot, and that these extractions are done at fixed value of x is equal to 0.1 and q is equal to 4 GeV. The data indicates that there is a clear distortion in the distribution of these U and D quarks away from the center, that is due to the Sivers effect. So for these analyses, either in zero prescription or GPM or in CSS formalism, they have improved our understanding of Cox-Sivers function without any doubt. However, one can ask that what about the gluon-Sivers TMD? Gluon-Sivers function is not known fully, though initial attempts have been made by Collier group since 2015, and they extracted the gluon-Sivers function by using the Pi0 data from RIC. And they also extracted the first moment of the gluon-Sivers function using the Midrapidity data from Pi0 and D0 data. However, due to the few data points from these processes, one cannot control the gluon-Sivers function over the wide range of x and k probe. Therefore, EIC, which is going to operate at US, could play a vital role in shaping the gluon-Sivers function. In order to understand more about or advancing understanding about the gluon-Sivers function, we propose the inelastic leptoproduction of WG5 at EIC for probing this gluon-Sivers function. At EIC, the energetic electrons are bombarded on a polarized proton. The radiated virtual photon from the initial lepton will interact with the constant of the proton that produce the final state WG5 along with the scattered electron. At EIC, the WG5 production has been advertised for the probing the gluon TMD since its discovery. At EIC, the WG5 is produced by the fusion of the virtual photon and the gluon, and that produces a heavy charm and anti-charm quark pair in a going quantum state. This can be calculated by using perturbation theory. Now this produced heavy charm and anti-charm quark pair transmit into the physical quarkonium by emitting or observing the soft gluon that is denoted in this blob. This happens at the scale below lambda QCD. Depending on how you treat this perturbability or non-perturbability part, there are three models that are widely used in the market. One is color simulate and color evaporation, and the third one is the non-relativistic. These two models have been already discussed by Mariyah. Let me not go into details due to the constraint and time. In our calculation, we considered 12 Feynman diagrams, including the quark channel, and we considered the color simulate and NRQCD formalism, in which the different cross-section is factored into perturbability piece, which is contains in d sigma hat times the long distance matrix element. Moreover, we consider two models. One is generalized pattern model, and the another one is the color gauge invariant GPM model for the TMDs. In the GPM, we do not consider any final or initial state interactions, and the corresponding color factor for those Feynman diagrams in GPM is denoted with C subscript U, and its corresponding hard part is denoted with H superscript U. Now we switch on the interactions. Due to the colorless nature of the photon, we do not have any initial state interactions. We consider the single iconogluon approximation. This iconogluon is attached to the final heavy charm and anti-charm quark pair as shown in these Feynman diagrams. Due to the extra color flow into these Feynman diagrams, the color factors are modified, and which is denoted with the CF superscript F/D. However, one can observe this modified color factor into the hard part as shown in this equation. In GPM, we have one universal gluon-Sivers function, whereas in CGI, we have two independent but which are process dependent gluon-Sivers function. One is F-type and D-type. These two independent Sivers function are actually basically related to the how you neutralize the color in the Feynman diagrams. There are two ways one can neutralize the color using the symmetric structure constant and the antisymmetric structure constant. Moreover, we have found that when the heavy quark pair produced in the color singlet state that do not contribute to the asymmetry due to the cancellation between these two Feynman diagrams. However, only color octet state do contribute to the asymmetry. Here, the color factors for in GPM as well as in the CJ are given for both quark channel as well as the gluon channel. One can see that the color factor associated with D-type gluon source function is always 0. This implies that Gypsy production at EAC is a potential channel to probe the process-dependent F-type gluon source function. One can see that when the heavy quark pair produced in the color singlet state, as always, the color factors are 0 in CJ. That's what we are showing here. Here, the standard kinematical variables for the CDs are shown. We consider the centromast frame of the electron-proton system. In this diagram, the phi s is the azimuthal angle of the polarization of the proton, and phi s is the azimuthal angle between the lepton and hadron plane. The Sivers asymmetry A sub n is defined as this. The denominator part is basically 2 times the unpolar differential cross section. We consider generalized Potter model framework and assume that the factorization is valid. Having done that, the numerator part can be written in this form, where Xa is the momentum fraction and its of the photon and its corresponding transverse cathode. Delta F hat is the Sivers function. The unpolar differential cross section can be written in this, where Fa slash is the unpolarized photon TMD. L mu is the standard electronic tensor, which is rewritten in terms of this form for the computation purpose, where P mu is the 4 momentum of the initial 4 momentum of the proton, and L pop mu is the transverse unit vector of the initial lepton. The terms which are proportional to the Q mu are dropped due to the gauge condition, where Q mu is the 4 momentum of the photon. The hard part, which is denoted with HU, which is calculated by using NR-QCD framework. The last piece of information that we need in this equation is the long distance matrix element. There are different LDMD sets that are available in the literature, which they impose different kinematic cuts to extract those LDMDs. However, we consider 2 sets from these 2 processes, which we call BK11 as well as SY13 LDMD set, in order to explain the low PT data that we are interested in. For numerical purpose, one need to parameterize the TMDs. We consider the GPM in which the unpolarized TMD is factorized into the collinear PDF times the Gaussian form. Similarly, the the Sivers function is parameterized in this form. We give the maximized Sivers asymmetry results. Further, the Sivers function has been saturated by taking the rho is equal to 2/3 in this equation, and the n here is taken to maximize, plus 1. With this choice, we can still satisfy the positive bound on the Sivers function. The free parameters in our theory are the Gaussian width and the long distance matrix elements. 0.25 GU square is for quark and 1 GU square for gluons are taken for Gaussian width. In these plots, the unpolarized differential cross section as a function of transverse momentum of the Gypsy is shown at the center of mass energy 318 GeV, and the data points, which are in black, are taken from H1 collaboration. The left panel is obtained by using BK11 LDMD set, while the right panel is obtained by using SY13 LDMD set. In these plots, the prompt means the direct as well as the feed-down contribution along with the QD diagrams as well as intrinsic charm contribution in the proton. The green dash curve represents the QD diagrams contribution, which contributed the order alpha cube. The pink dotted curve represents the intrinsic charm contribution to the Gypsy. The color singlet model prediction is denoted with the green dash dotted line, while the red solid curve represents the NR-QCD prediction. And the band is obtained by weighting the factorization scale from 2 times transverse mass to the half of the transverse mass. For feed down, we have included the Psi2s, while the Chi-C and B quarks are dropped due to its insignificant contribution compared to the Psi2s. The long distance matrix elements for Psi2s are taken from Sharma 2013 paper. Here we have given the unpolar differential cross section as a function of U square and W and Z, as shown at the center of mass energy 380 GeV, and the data taken from H1. The legends of these curves are same as the previous plot. Within this kinematical region, we are in good agreement with the data. Here, the prediction for the EIC, the unpolar different cross-section as a function of PT is shown at the center of mass energy is 45 and 140 within this kinematical region. Now we are coming to the Sivers asymmetry results. A sub n as a function of PT and Z is shown both in upper panel and left panel, lower panel for BK11 as well as Xiaohui LDMD set at EIC 45 GeV. In all these plots, the red solid curve represents the gluon channel contribution to the asymmetry within the GPM framework using an QCD framework, while the light blue dash dotted curve represents the F-type gluon Sivers.
Rajesh, you have 3 minutes.
Okay, thank you. I'm going to finish. Thank you. The light blue dash dotted line represents the F-type gluon Sivers function contribution in the CJ within the inner QCD framework. The quark contribution both in CJ and GP are so tiny compared to gluons, and the BK11 LDMD set predicts about maximum 25% of asymmetry, while in CGI, the asymmetry is drastically reduced due to the absence of 3s1 color singlet state, as well as the suppression of the color factors. Whereas the SY13 set predicts about maximum 15 to 17% of asymmetry. And this indicates that there is a clear choice, there is clearly dependence on the choice of LDMDs that we use. In the lower panel, asymmetry as a function of G, Z is shown, where Z is the inelastic variable that carries the energy fraction of the jet set. Here, the asymmetry as a function of PT is shown at the center of mass energy compass 17.5 GeV. We have one data point from compass collaboration, though its uncertainties are very large. Still, we compared our estimation with the data. This brings to the summary of my talk. We have studied the Sivers asymmetry in inelastic leptoproduction of jet at EIC by incorporating the generalized pattern model as well as the CGI model. The GPM predicts sizable asymmetry, while the asymmetry in CGI are drastically reduced. The sizable asymmetry indicates that the jet is a promising channel to probe the unknown gluon Sivers function. Moreover, it allows to probe the process-dependent F-type gluon Sivers function. Interestingly, our unpolarized different cross-section estimations are in good agreement with the data within the low PT region. Thank you for your attention.
Thanks, Rajesh, for the nice presentation. And the talk is now open for questions. Alexei.
Hello, do you hear me?
Yes.
Could you please go to the slide with the formula for cross-section? It is slide 11. Yes, so am I right that all evolution which you have is actually concentrated in evolution of TMDs? Sorry, in this, please go to next formula, sorry, next slide. Is concentrated in evolution of your collinear PDFs, so you have only mu.
Yes, yes.
So do you have any non-perturbative TMD evolution?
Yeah, so at the moment, by assuming this generalized pattern model, we do not have any non-perturbative effect as we do like a clear TMD evolution. So at the moment, we are just restricting to the evolution within only the collinear PDF. But so we wanted to do that.
So in turn, it means that actually your asymmetry is not evolving. Yes, it is independent on Q. Is it right?
At the moment, you can say, but since the asymmetry is ratio, we don't know how much that would affect that you are saying that TMD evolution could really affect that. One could see, but still it's a ratio, so maybe the non-perturbative effect both in numerator and denominator could cancel, but still.
No, I mean just so since your unpolarized TMD and Sivers TMD both proportional to just so the mu evolution is given by just usual deglab. This factor just cancels from denominator and numerator.
Yeah.
So there's no trace of Q anymore.
Yes.
Okay, that's all what I want. Yeah. So thank you.
Thank you.
Caroline.
Yeah, hello, this is Caroline, and this is related to a question that came up in the plenary session yesterday.
Yes.
If you could go to the page with the compass data point. And here a compass has two data points, one at this set value that you show, and then one at higher set, so at 1 basically. And the question, Yeah, whether this basically exclusive data point is also still sensitive to the gluon Sivers, or whether that would rather be in the generalized Parton distribution range, because it's exclusive, because you only show this lower Z point. Can you comment on that?
Yeah, okay. So at Z is equal to 1, actually we will have the infrared divergence. So that's why we are restricting our Z from 0.3 to 0.9.
I see. And in principle, would the data point at high Z still be sensitive to the gluon Sivers, or is this just excluded from your framework?
Yeah, since I wanted to say that here we are considering the Platonic channel that we have is the virtual photon plus gluon that goes to CC bar plus another final gluon along with the jet side. So that's why we have infrared divergence. The final gluon becomes soft when Z goes to 1. However, you can consider the leading order process where you have virtual photon plus gluon that goes to only the jet side. That process actually contributed Z is equal to 1.
Okay.
In that case, you can take the data point and compare with that.
I see. Okay, thank you.
Yeah, if I may comment a bit
Please.
on that. So actually for this process, virtual photon induced process at this order, where you also have a gluon produced in the final state, the region Z equal to 1, the point Z equal to 1, if you want to make a theoretical estimate also including that point, then you need to take the virtual corrections to cancel this infrared divergence. So a complete next to leading order calculation would include that point, which we haven't done here. So we basically impose a cutoff on Z to avoid Z equal to 1 region.
I see. Okay.
That's right, Rajesh. You have imposed
yes,
a cutoff, right?
exactly. That's what I want to say.
Any other question?
May I ask a question?
Yes, who is it? I don't see
It's
your hand.
Alexei. I raised hand, but it wasn't distinguished. So it may be a naive question. Maybe I missed it during talk. So, but am I right that here I see Q bigger than 0.03? I mean, you really evaluated it at that small Q? I mean, I'm looking at this slide and observe this
Okay.
line.
Actually, they have given in so this kinematical cuts we have taken in line with the data point. I mean, they included the Q value from very, very low. Means basically they included the photo production events also. I would say.
Yeah, but how did you evaluate it? I mean, usually if you apply such formulas, you just have Landau pole. How did you avoid it?
I think Q square is not the scale for Parton distribution evolution here, right, Rajesh?
Yeah, we are using the transverse mass of the scale.
Yeah, so this is not the evolution moment.
Okay, thank you.
You can see here, this is the scale of the PDF.
I see.
The alpha
Okay.
is.
Okay.
And Q
Thank
square
you.
is the photon. Yeah, watch it.
Yeah.
Okay, thank you.
Yeah, thank you.
Other questions? Any other questions? I don't see any hands. So let us thank Rajesh again, and we move to the next talk, which is by John Terry.
Hello, can you hear me?
Hello, John.
Hi, 1 second. Okay, do you see my screen?
Yes, could you please make it full screen?
Yes, 1 second. Okay.
Perfect.
Okay.
Yeah.
So first, I'd like to thank the organizers for the opportunity to present here. My name is John Terry. I'm a fifth-year PhD student at UCLA. For this talk, I'll be discussing our recent paper, which is titled QCD Evolution of the Gluon Sivers Function in Heavy Flavored Dijet Production at the Electron-Ion Collider. If you have questions, you can see, for instance, our paper You can also send me an email or ask me questions, of course, at the end of the talk. So we've already seen quite a few talks on the Sivers function, but I wanted to provide some background just to give context. So the Sivers function is a TMD PDF. So it provides information about the three-dimensional structure of hadrons. Namely, it provides information about how the introduction of a transverse spin affects this three-dimensional motion of quarks and gluons. Now, an interesting complication associated with the Sivers function, this is something that Rajesh just mentioned, is that the Sivers function is process dependent. So the most famous example of this process dependence is, for instance, the Sivers function in Zhanwen and semi-inclusive DIS. So this occurs because the gauge length that enters into Zhanwen is generated by the interaction of the incoming antiquark with the polarized proton's remnant field. So as a result, you have a past pointing Wilson line. Whereas in semi-inclusive deep inelastic scattering, this Wilson line is generated by the interaction of this outgoing quark and the polarized proton's remnant field. So as a result, you have a future pointing Wilson line. So experimental verification of this sign change was first performed by the COMPAS collaboration in 2015. So it turns out that the process dependence for the Gluon-Sivers function is actually much more complicated than for the quark-Sivers function. So there are two types of Gluon-Sivers functions. The first is a dipole type or D-type Gluon-Sivers function. And this is measurable, for instance, in pp to gamma plus jet. And you can see, for instance, just by studying the partonic channel, that the Wilson line for this process looks as follows. The second type of Gluon-Sivers function is the Weizsäcker-Williams or F-type Gluon-Sivers function, which is measurable, for instance, in EP to heavy quark pair production. And again, by studying the partonic channel, you can see that the Wilson line for this process looks as follows. Now, the interesting thing is that despite the fact that we start this process with the exact same initial state, and we're seemingly probing the same distribution, these functions can actually have different behaviors. You can see, for instance, in this paper here, where they discuss different asymptotic limits, in particular at small x, that these two functions can behave very drastically differently from one another. So in order to understand the Gluon-Sivers function entirely, we need to probe this distribution function, both in collisions such as pp to gamma plus jet, and also, for instance, at the EIC, we can study, for instance, EP to QQ bar. And then a second point that I wanted to make is that in order to verify our current understanding, our theoretical understanding of the Gluon-Sivers function, another measurement which could be performed as a verification is to study the Gluon-Sivers function, for instance, in EP to heavy quark pair production versus PP to diphoton production. So exactly analogous to the quark-Sivers function, because the Wilson lines for these two processes point in exactly opposite directions, and they're both F-type Sivers functions, we expect that there's modified universality between these two functions. Okay, so I've discussed the fact that we want to perform a measurement of the Gluon-Sivers function at the EIC, but is that feasible or not? So that study was actually performed in 2018 in this paper here. And this was done using a Pithier reweighting analysis. And they studied the Gluon-Sivers asymmetry in three different types of processes. The first is open charm pair production, dihadron production, and then also dijet production. So for each of these processes, these authors studied this Gluon-Sivers asymmetry at an integrated luminosity of 10 inverse femtobarn. And what they found is that the Gluon-Sivers asymmetry, for instance, in open charm, is essentially consistent with 0. So in their analysis, what they did is they chose as a proxy for open charm these D mesons, which have a decay signature of D decay pi. What's happening here is that the branching ratio for D decay pi is roughly 3.7%. So as a result, you need really high statistics in order to be able to see the asymmetry. The second process that they studied is dihadron production. So here they're plotting their asymmetry as a function of XB. And there are two important features of this plot that I wanted to point out. So the first is this black line here. So this is the parton level asymmetry. And the second are these black dots here, which represent their projected asymmetries, which are measurable, or their simulated asymmetries. And you can see that relative to the parton level asymmetry, their projected asymmetry is reduced by a factor of 3. And they state that this effect is occurring because of complications associated with the fragmentation of light quarks. And then the third and final process that they study in this analysis is dijet production. So they do dijet production for light flavor, and there are two contributions. One is coming from photon gluon fusion. The second is from photon quark fusion. And again, they're plotting their asymmetry here as a function of xp. And again, with this black line represents their parton level asymmetry, whereas these black dots represent their projected asymmetry. And you can see that in dihadron, for instance, the parton level asymmetry is reduced by a factor of 3, whereas in the dijet case, the parton level asymmetry is reduced only by a factor of 2. So the conclusion that was made in this paper is that the dijet channel is actually the best channel for measuring this parton level asymmetry at the Electron-Ion Collider. Now, because they measure this asymmetry in light flavored dijet production, there are actually two contributions that enter a leading order. So you can have the quark contribution, which is given by these red lines down here. And then there's also the gluon contribution, which is given by these black lines here. Here they plot for different values of q squared. And you can see that even at relatively small values of x, it's actually a pretty significant background, which is coming in their analysis from the quark-Sivers function. So in order to isolate a gluon in the initial state, we decided to study the dijet imbalance for heavy flavor dijet production at the Electron-Ion Collider. We can establish a factorization and resummation formalism for this process using soft collinear effective theory by assuming a power counting. So we assume that the PT of the jets is large. We assume that PTR, PTR is much smaller than PT, and that PTR is the same order of magnitude as the mass of the heavy quark. We then assume that QT is much smaller than PTR, and then finally we assume that QTR is a consequence of making this assumption that PTR is much smaller than PT. We also have the assumption that QTR is much smaller than QT. So using a simple mode analysis in soft collinear effective theory, you can, the differential cross-section for the unpolarized case, it has the following form. So we have a hard function, a soft function, a TMD PDF. We have two jet functions, one here, and then we have also our collinear soft functions. These collinear soft functions contain information about soft radiation which exits the jet, and these can contribute also to the dijet imbalance. So because of our power counting assumption that the mass of the heavy quark is much smaller than PT, the hard function, also the soft function that enters into our factorization theorem, is actually the same as for light flavored dijet production. And then, however, the soft collinear function, also the jet function, these are sensitive to the mass. And so what we did in our analysis is we performed a calculation of these perturbative ingredients at next to leading order in QCD. So these first two plots here represent the real corrections to the heavy quark jet function, whereas these right plots represent the virtual corrections. So performing a calculation for these ingredients in next to leading order, we derived the anomalous dimensions for this mass-dependent jet function at next to leading log. And then similarly, the mass-dependent collinear soft function. So here I've provided a plot of the graphs at next to leading order. And then after performing explicitly this calculation at next to leading order, we can perform the calculation for the collinear soft anomalous dimension at next to leading log. So renormalization group consistency in the case where the mass goes to 0 was already shown in this paper here in 2020. What we find in our analysis actually is that if you add the anomalous dimensions of the jets, the heavy flavored jets, and also the collinear soft functions, that the mass dependence actually exactly cancels out. So the sum of our anomalous dimensions is equivalent to the massless case. And this is exactly what you need to require in order for renormalization group consistency. So what we find in our analysis is that our factorization resummation formalism is completely RG consistent. Okay, so far I've discussed the factorization theorem for the unpolarized case. How do we get the factorization for the spin-dependent case? It's actually quite simple in soft collinear effective theory to do this. So we can simply replace the unpolarized TMD PDF with the gluon Sivers function. We simply make this replacement, and then we know that the anomalous dimension for the Sivers function and the anomalous dimension for the unpolarized TMD PDF is the same. We also know that this holds for the rapidity anomalous dimensions for these two functions. So Okay, so now we made this replacement. So one of the things that Rajesh mentioned is that when you calculate the process dependence for the Gluon-Sivers function, you also have to consider attaching this gauge link to these external particles over here. So what do we do? So in order to consider also the hard part, what we do is we can write the hard function for this process as an unpolarized color factor times some kinematic function, and then there's this delta AC, which I'll discuss in a minute. It just enforces that the color entering and exiting, exiting and entering the gluon-gluon correlator has to be the same. And then over here we have two attachments. One is to the heavy quark and one is to the heavy anti-quark. And so as a result, we have two color factors that are entering into this hard function. We have a minus I FABC that I'll discuss in a minute. And then we can write this as a kinematic part. Again, what we find, so this delta AC and also this minus I FABC, this should be absorbed actually into the definition of the unpolarized TMD PDF and the Gluon-Sivers function. And so what we recover at the end of the day is that the color factor entering into the unpolarized process and the sum of the color factors entering into the polarized cross section or the polarized hard part are exactly equal to one another. So this is an indication that the hard functions for the unpolarized case and also the polarized case are exactly equal to one another. So we took this as indication that the hard anomalous dimension for the polarized case is equal to the hard anomalous dimension for the unpolarized case. Okay. So I mentioned 2 slides ago that the mass dependence and the sum of the anomalous dimensions exactly cancels one another. But I wanted to make the statement, this doesn't mean that the mass dependence,
sorry, you have 3 minutes.
3 minutes, okay. This doesn't mean that the mass dependence exactly cancels into the cross section. So what's happening is that we evolve our jet function from the natural jet scale up to the hard scale. We also evolve the collinear soft function from its natural scale up to the hard scale. So there's the natural scale of these functions is not the same. So as a result, there's some miscancellation that's occurring here. So we do some phenomenology just to look at the size of the mass corrections for this process. We take the following parameterization. We take the following value for the PT and the following value for the absolute value of the rapidity of the jets. So here we're plotting our unpolarized asymmetry for the charm jets and the bottom jets. This is the normalized QT distribution. So this solid line represents the case with the full mass dependence, whereas these dotted lines represent the case with no mass dependence. And you can see that there's small corrections coming in for the charm jets versus relatively large corrections which are coming for the bottom jets, which is what you would expect. And then finally, we also perform some proof of principle phenomenology for the Gluon-Sivers function. We chose the following parameterization, which was taken from this paper here. And this is for the collinear parameterization. For the TMD, we choose the following parameterization, which is given here, which is consistent with this paper. So here we're plotting our asymmetry as a function of Q perp over P perp. And again, the solid lines represent the full mass dependent case, whereas these dashed lines represent the case without any mass corrections in the resummation. And again, we see that for charm jets, the size of the correction coming from the mass is quite small, whereas for the bottom jets, it's much larger. Okay. So just to give a conclusion, so we generated a factorization resummation formalism for heavy flavored dijet production. So we consider mass corrections to the collinear soft, the exclusive jet function, also the resummation formalism. So we've generated some predictions at the EIC, some proof of principle predictions at the EIC. And we expect that possibly, over the large kinematic regions at the Electron-Ion Collider, if you wanted to perform a global analysis of the Gluon-Sivers function, these mass corrections could prove important. Thank you.
Thanks, John, for a nice talk. Any questions? Any questions for John?
No questions?
I do not see any raised hand. So in the chat box, oops, sorry. There is a discussion going on, but it's about the previous talk. Okay, so if there are no questions, let us thank John once more.
Thank you for
I
your
had a
time.
question for John.
Sure.
Okay, please go ahead.
John, Harry.
Oh.
Just have one. So in your class, do you consider evolution in this stuff? In
Yes,
these,
of course. Yes, yes.
So it is a next leading order evolution, what you put? Or?
This is next to leading log, so we don't do the next to leading order, the finite part of the next to leading order piece.
And have you an idea of the error bands that can?
Yeah, I mean, so we're currently checking that. Yeah, at the moment. Yeah, it's a good question. I guess your question is whether or not, once you include the error bars, can you differentiate, for instance, the massive case?
Yeah, for instance.
Yeah. So that's something that we're currently checking. At least at the current perturbative order, we don't know, for instance, if you can differentiate these two, but we expect that as you go to a higher perturbative order, that you should be able to differentiate them. It's a good question.
Okay, thank you.
For the question, anyone else wants to ask a question? Okay, if not, then let us thank John once more and let us move to the last talk of this session.
Thanks again.
Which is by Xiaohui Liu. Okay. So we can see your slides. If possible, make it full screen.
Sure. Okay, thanks. So
Yeah.
Can you see my slide?
Yeah, start please.
Okay, thanks. Okay, so I'm going to talk about using the jet charge to map out the flavor information for the spin physics. Okay, so we know that there have been lots of efforts recently devoted to these jet probes of the nucleon structures at the EIC. So one advantage of using jets is to reduce the non-perturbative degrees of freedom. For instance, if we use the jet probe of the proton initial TMDs, compared with cities, we can get rid of this non-perturbative fragmentation function, but replace that with a jet function, which is purely a perturbative ideally. So this potentially can help us to have a relatively cleaner or easier extraction of the polarized or unpolarized TMDs. So currently for jets, in this kind of scenario, the factorization is evaluated at next to leading log level, whose accuracy is a little bit lower than the cities. But just recently, we pushed the calculation of the jet function to next leading order for anti-KT, which potentially allows for a next leading log resummation to be comparable with the cities. So far, everything seems to be nice for the jet probes. But how about the flavor separation? So at some point, we know that at the EIC, we want to know the information, for instance, the spin information or the TMD distribution for a specific parton flavors, which requires some kind of flavor separation. The flavor separation seems to be almost impossible for jet probes because we know that the jets are almost inclusive over the final state hadrons and therefore should be completely ignorant of the flavor information. So the situation is very different in cities. When we use cities, it's very natural for us to achieve this kind of flavor separation. For instance, if we tag a pi plus in the final state, we know that we are probing more or less the U quark in the proton and a pi minus for the D quark. But of course, here we pay a price. We pay a price in the sense that we have to extract the TMD distribution and the TMD fragmentation function simultaneously. And the TMD fragmentation function by itself nowadays is still poorly constrained, and it's actually very hard to extract. So now the question is, are there any other alternatives to realize this kind of flavor separation without introducing extra non-perturbative distributions? We know that for distributions, there are too many degrees of freedom, therefore it's very hard to, relatively hard to constrain. And also we can ask ourselves, is it possible for us to directly use the jets to realize this kind of flavor separation? So when we talk about flavor separation or the difference between different proton species, very likely the first thing comes into our mind is the quark electron charge, right? So this is pretty much the reason why we can tell the difference between a U quark and a D quark. So the question is that possible this kind of protonic electro charge information can be propagated into the final state jets without being washed out by the hadronizations or the contaminations? So the answer to this is luckily yes, but if we can define the jet charge in a proper way. So it turns out that a proper definition of the jet charge was given a long time ago by Feynman. So what he did is he reweighed the hadron charge within the jet by the hadron momentum fraction with respect to the jets. So here kappa is a free parameter. And if you notice that for this overall factor, the overall factor is actually used to suppress the soft contaminations. Because for relatively low energy contaminations, this overall factor is almost negligible. Therefore, its contribution to the jet charge could be vanishing. And of course, eventually with some overall hadrons in the jets. We have another flexibility to restrict this summation over a specific hadron species. For instance, we can set all the hadron charges to 0 except for the pion. In that sense, we just define the jet charge using the pion formation, and we can do the same thing for the kaons. In other words, the jet charge actually provides a method for us to study the hadrons within the jet collectively, instead of say, let's tag a hadron once at a time, which leads to the fragmentation function. In any case, this is the jet charge observable we are focusing on in this talk, and will be used for the flavor separation. And you will see that it's actually very efficient in doing this flavor separation. As you can see from this PCS simulation with kappa equals to 0.3. So here I show the U quark jet and the D quark jet jet charge spectrum. And you can see they peak differently in the positive and negative charge region as expected. And also those peaks, they are well separated. So this simulation is also further confirmed by the Atlas real data analysis, in which you see again, the U quark jet and the D quark jet are very well separated by the jet charge. And also notice that the jet charge defined in this way is pretty much independent of the jet PT. It's pretty much just a constant. So these studies indicate or suggest that the sign of a protonic charge is largely inherited by the jet from the initiating proton. The jet information, especially the sign of the charge, is robust against the hadronization. And from this event fraction of the jet charge, we notice that we can realize very good U and D quark separation by just dividing the events into different charge rings. Okay, and this kind of event fraction of the jet charge can be related to the spin asymmetry via the factorization. So here is the factorization theorem. For the time being, you can ignore all those notations here, just to focus on the final conclusion. So the factorization theorem states that for almost the back-to-back electron and jet production with very small imbalance QT in the TMD factorization, the cross-section with the jet charge measurements can be related to the conventional cross-section without the jet charge measurements by multiply each protonic channel a factor Ri. So here Ri is nothing but the event fraction in a given charge beam, as seen in this plot. So some comments for the Ri. Ri is non-perturbative, but luckily it's just a number for each given charge beam instead of a distribution. And also for different protonic channels, Ri can be associated via the flavor symmetry, which will dramatically reduce the number of degrees of freedom used for global fitting. And also Ri is universal in the sense that the Ri you extract from EIC will be the same as the Ri you extract from the LHC. So the behavior of Ri will be very similar to the NRQCD Quaternion matrix elements. So by reading this factorization theorem, we realize that by choosing correctly the charge beam, we can actually control our sensitivity to different partonic flavors through this the relative size of this R. So with this factorization at hand, let's study some numerical consequence. So we choose kappa equals to 0.3 to have a relatively good separation in the peaks. And also when we define the jet charge, we focus on, we choose the pion component of the jets. We further divide the jet charge into 3 different beams: the positive beam, the negative beam, and the zero beam or neutral beam. Depends on how the whether the jet charge is greater than 0.25 or less than minus 2.25 or some numbers between them. For our theoretical study, we just use PCA simulation to extract those event fraction Ri. So for instance, if you look at the U fraction in the positive charge beam, you find that it's almost identical. It's actually identical to the D event fraction in the negative charge beam. This reflects the asymmetry, the flavor symmetry I just mentioned, which will be very useful for reduce the parameters need to be extracted from a global fitting. And also, if you look at the second row, you notice that the U contribution to the negative charge beam is highly suppressed compared with the D contribution. And therefore, we will expect an enhancement of the D quark contribution in the negative beam. And also, we note that if instead of using pions, if we use kaon component of the jet, we will expect an enhancement for the strange quark. Okay, now let me show a example of the sensitivity of the spin asymmetry to the D quark Sivers function at the EIC. So we studied this by looking at how the spin asymmetry will change if we entirely remove the D quark contribution from the polarized cross-section. So this upper panel shows that if no jet charge is measured, shows the case if there is no jet charge is measured. We see that in this case, removing the D contribution results in a very small change in the spin asymmetry. And this change is almost comparable with the theoretical errors. So this indicates that if no jet charge is measured, the spin asymmetry is insensitive to the D quark flavor. So the story dramatically changes if we look at the negative charge beam, where a huge jump in the spin asymmetry is observed when we remove the D quark contribution. So this implies that it dramatically improved the sensitivity to the D quark in the negative charge beam, and the jet charge does do its job in the flavor separation. So now let me just conclude. I hope I persuade you guys that the jet charge can map out the hadron component of the jet collectively, and thus serves as a proton flavor separation for TMD physics. And also here's some comments for the jet, for the spin physics. So unlike the jets at the LHC, the jets for spin physics, the energy of the jets for spin physics are relatively low, usually relatively low. Therefore, the non-perturbative part of a jet could be sizable and sometimes even dominant. And actually, those non-perturbative part of the jet is quite interesting and also useful for the so-called fermitography of the nucleon. So the jet charge is one example, as I have extensively discussed in this talk. Another example is the so-called time reversal odd parts of the jets. So this T-order jet allows us to probe more spin structures, which we don't expect it from normal unpolarized jets. And also it serves a way to be sensitive to different hadronization mechanisms by manipulate or use different jet algorithms. So I think that's all what I want to say. Thanks.
Thanks, Xiaohui. So the talk is open for questions. There are 3 hands. First, I don't know which one was first. Songling, please.
Yeah, thank you for the talk. I think if that time you mentioned you separate the charge into the -0 and plus, and why you can separate in that way, and why 0.05 is a choice? Is that approximation? Why they are universal?
So it's really just based on our simulations. So if you look at this, so our goal is to separate the d quark, because u quark is usually always dominant because of its charge 2/3. So if you take a rough, we don't do it's not optimal. It's not the optimal choice. We just take a look by our eyes. So visualize this. So actually, if you look at d quark distribution, it's more or less peaked around -0.25. And then we just do the symmetric, and then we just make this symmetric to say, okay, if it's less than -0.25, it's minus jet being, if it's greater than 0.25, it's positive. And of course, we can do a likelihood things, which gives us the optimized value. And also for kappa equals to 0.3, it's not optimized. So in principle, maybe kappa equals to 0.5 is the best choice. Yeah. So it's very preliminary.
Okay, Alexei.
So my question about non-perturbative dependence of jet on KT, because in TMD factorization principle, you have, due to jet algorithm, some remnants of soft factor, and you also have some KT dependence on perturbative for jet, yes? So you seems to ignore it, but in general present. And my question was, does this RI couples to KT?
Well, it depends on frame choice. So in our case, we are looking in the central mass frame. So the jet is really energetic. It's in the central region. It's energetic. So for jet, actually, there is no KT dependence. If you look things in the bright frame, as proposed, like cities, for instance, right? So then there will be some KT dependence also in the jet function, as you can see by those. Oops. Sorry. Yeah, by work by.
No, I mean no perturbative KT dependence. I mean presumably.
I mean, perturbative KT dependence and non-perturbative KT dependence will be dropped from this factorization theorem if you just look at if you study the TMDs in the central mass frame, but in the bright frame. So because in the central mass frame, the jet PT is so large, it's insensitive to this small KT component. But if you choose another frame, for instance, as those gentlemen did in their paper for the WTA jets in the bright frame, in that case, you do have a KT dependence in your jet function. That's true. So it's all frame dependent.
Okay, thank you. That's clarified a lot. Yeah, thank you.
Dillon.
Yeah, thanks for the interesting talk. Could you go back to the slide that you were just on with the background fractions? Or I don't know if background fraction is the right word. You had different fractions for the different charges.
In this one?
A little bit further, where you had the table that had the different quark flavors.
This one, right?
Yeah, right here. So I'm interested in this last bullet point, expect enhancement of the S quark if the K-on component is used. So if this was the case, how would you actually then separate from down quark hadronization? Because they have the same charge, right?
Yeah, that's a good question. So for K-ons, it could, we do some study on this, but it's a while ago. So for K-ons, it does enhance a little bit it's not that dramatic. It's enhanced a little bit the strange quark contribution. At some point, yes, it's probably comparable. I cannot remember. It's probably it's S or S bar, maybe comparable with down quark or the other ones. It's not that suppressed, so it gives more sensitivity to the strange quark. It's not like this. It's not like for U and D. It's that dramatic. But just increased a little bit the sensitivity.
I see. So the distribution might not look like this symmetric bimodal type distribution. It would probably have an enhancement in the negative charge side.
Right. That's true.
Thank you.
Christine?
I have a follow-up question on that. So for K-on, measuring the K-on component, this would be only looking at K-ons or looking at Pions plus K-ons that you have in mind?
Well, when I'm talking about kaon, it's just a kaon. Instead, there is no pions. So basically, you set a pion charge to 0, and you map out only the kaons.
Okay, I would just worry that at the EIC, there'd be very few jets with multiple kaons in the same jet. I mean, I guess you could look at the charge of a single kaon, but okay, I'll just have to think about that with the relatively low multiplicities for jets at the EIC. I have another question though. I'm a little surprised that they're just looking at Ri plus for U and D, that you have these quantities circled, the 0.52 and the 0.53, so they're basically the same. I'm a little surprised that they're so similar, just because, so of course D bar is positive, but the magnitude would be different. I might have expected some difference in these R values due to the different magnitudes of the up and down charge.
Because the accuracy we keep, the precision we keep, they're almost identical, but actually they are slightly different. Actually, not that dramatic. It's just a slightly difference because so look at this is the this is the definition of the R. R is really, say, given a U jet, then what's the fraction of the given you a U jet, what's the fraction of the positive charge being, what's the fraction of the events falling to the positive charge being.
Mm-hmm.
So because of flavor symmetry, I think they should be close to each other.
Okay, I mean, I guess I was just the plus a third, sorry, plus 2/3 for you, and D bar would be plus 1/3. So that's what I was wondering about.
Well, that's normalized out because here it's really say, okay, I have one jet, which I know it's a U jet, then what's the fraction of this U jet in the positive charge being?
Okay. Okay, I would just think that the distributions, given your bin, like your symmetric bin cuts, I'll have to think about it more. Anyway, thank you.
Albie?
Yes, so thanks for this nice presentation. My question is about the definition of a jet charge. How does it depend on the number of particles of hadrons observed in an event? So if you have an event with low particle multiplicity, for instance, are you still able to separate so well the different quark contributions?
Well, that's a good question. If you have a low event, let me think. Well, I think it's all in, well, I think if you have a low event, for instance, so let me say this, so those R values are not perturbatively calculable, right? They have to be extracted from some experimental data. If you have a low event, you probably will have a very large error bars on those R values extracted.
Yeah, so sorry.
Yes, so here we just use a simulation so we can control the error bars. We can have infinite small error bars, but in practice, you need to extract this from some data points like this, right? If you have low events for the jet charge, I guess it will have a huge fluctuation on, because of statistics. There is a huge fluctuation on your measured Q value, and therefore, when you do the extraction of those R values, the error will be propagated into the R value.
Okay, thanks.
Any other question? Okay, if not, let us close this session. Let us thank all the speakers and to all participants for coming to this session. And there's a break now, and there's another screen session after the break. Thank you and bye.
Thanks, bye.